Hi everyone, I'm going to present the paper The Sprawlter Graph Readability Metric, Combining Sprawl and Area-Aware Clutter. My name is Zipeng Liu. I'm from University of British Columbia. This work is done with Takayuki Itoh from Japan, Jessica Dawson, and Tamara Munzner from UBC. Node-link graph is a really popular visualization to represent the network structure. And one of the important quality measures for a node-link graph is readability. Readability measures the ability of a human to read a graph, such as how good you can trace a path. It is historically called aesthetic criteria in previous work. The most famous example can be the number of edge crossings, such as in this layout, there are number of two edge crossings. The reason we care about this metric is that it can help us evaluate layouts and eventually help us make good layouts. We identify a few problems in existing readability metrics. First, most of the metrics are about integer crossing counts, such as node, node edge, and edge crossings. These counts lack the precision of the amount of geometric overlap. In these two layouts, there are exactly 5 crossings between the blue nodes and the red nodes. But obviously, in the second layout, the situation is worse because the blue nodes are almost on top of the red nodes. But the counts does not tell the story. Second, most counts only consider single level structure, which means they ignore the meta nodes, while they are actually more visually salient. The same example here, I'm using a bounding circle to represent the meta nodes. You can see that on the second layout, there are more overlap between the blue big circles and the red big circles. Third, most metrics only consider clutter, which means they ignore the sprawl or geometric sparseness. We use the term sprawl to describe the situation where you have very small nodes and very large canvas, where it is really hard to read a graph. And it is really hard to encode things like a label inside a node. So using the same graph here, we actually shrink the size of the nodes such that you cannot see any labels inside it. To address these problems, we have a few ideas. We want to have a more precise clutter metrics, and we want to account for metanodes or multi-level structure. We also want the metric to combine clutter and sprawl. In this paper, we propose 2 new metrics to do so. So first, a new area-aware clutter metric to address the first 2 problems. This metric measures the area or angles of an overlap and maps it to a penalty score with a penalty mapping function. We implement these metrics for node, node edge, and edge crossings. The second metric is a Sprawlter metric. Sprawlter is a term combining sprawl and clutter. It will address the third problem, the clutter-only problem. The Sprawlter trades off sprawl and area-aware clutter with a geometric mean. We evaluate these 2 metrics against baseline metrics with 56 graph layouts generated from 13 datasets and 7 layouts, including some algorithmic approach and manual positioning. There are a lot of related work on readability metrics. We roughly categorize them into 2 bins, single-purpose ones and compound metrics. For single-purpose metrics, most of them are about single-level clutter, such as edge crossings. As I mentioned before, it does not account for the amount of geometric overlap. There are some work deals with edge crossing angles, but this one does not account for a just touching case, which I will talk about later. There are much less work on multi-level clutter than propose the group overlap, but it does not account for clutter between metanodes. It only accounts for clutter between metanode and leaf nodes. There are some work on sprawl or geometric sparseness, like compactness by Kiefer and visualization coverage by Dunn. Actually, we use the same definition as theirs, but they do not integrate sprawl and clutter. For compound metrics, most of them are implicitly used by layout algorithms, such as GEM, limlog, and Itoh. Note that these layout algorithms does not provide explicit quantity about readability. Another category is explicitly combined metrics, such as using weighted sum of single-purpose metrics. But this work does not say what weights to use. Our Sprawlter metric falls into this category, but it uses geometric mean, which is an exact way to how to combine the clutter and metric. Next, we're going to introduce the computational pipeline of Sprawlter metric. There are a few steps. First, we measure the geometric overlaps between the graph elements, such as a node and node, denoted as X. Second, we're going to map these measurements to penalty score with a penalty mapping function f of x. Third, we're going to sum up all the penalties as area-aware metric. Fourth, we're going to combine the clutter with the sprawl using a geometric mean. So in the first step, here we list out the three case node overlap, node edge overlap, and edge crossings using area, length, and angle. So from left to right, you can see that the two graph elements are overlapping with each other more and more. We distinguish these four cases as none, near min, sum, and near max case. Once we have the measurement, we're going to map them into penalties. As a baseline, the count-based metric produce 0 for the none case, but it cannot distinguish the near min, sum, and near max because it is all 1. For our penalty mapping function, we also want it to be 0 for the none case, but we want the ability to distinguish between the three cases on the right. So the first requirement to achieve this goal is to have a substantial touching penalty, which means in the near min case, the minimum penalty should be strictly greater than 0. Second, we want to have an increasing penalty if x is increasing. Specifically, we want to have a max penalty where the max penalty is strictly greater than the min penalty. We also want this penalty function to calibrate to the count-based metric, which means we want 1 to be between min and max, corresponding to the sum case. Finally, we want this function to be a local function, indicating that the pairs of nodes with different sizes should have different penalty functions. We pick some specific values for this mapping function and result in this general equation. So M is a constant, which is the maximum possible overlap. It defines the domain of the function. We have a few parameters in this equation. So gamma, it defines the curve shape of a power function. You can also say that f of x is linear to a power function. This is inspired by the Stevens psychophysical power law from in perception. We also have alpha and beta to control the minimum and maximum penalty. There are more details in the paper and supplemental material. You can check it out for detailed analysis of these parameters. So once we have all the penalties, we can sum them up as the area-aware metric. Finally, we want to combine the clutter term with sprawl. Note that we are using the same sprawl as previous work, which is dividing the total join area by the area of all nodes. So here's an illustration of this equation. The sprawl for this layout is the bounding area over the area of the union of all nodes. When we combine clutter and sprawl, we want this metric to have the following properties. It needs to be high for bad cases. Some of the example bad cases are when you increase sprawl to reduce clutter, which, for example, you can push the nodes away from each other to reduce clutter. Another case is you can have compact space usage, but a lot of overlaps, meaning high clutter. We also want the Sprawlter metric to be low for good case, such as when you have low sprawl and low clutter at the same time. To achieve this, we use a geometric mean to combine these two terms. The geometric mean can normalize different ranges of sprawl and clutter. And the term with a max function is to floor the clutter above 1 to retain sprawl when there is no clutter, because we're using a product. For evaluation, in a high-level sense, we have a quantitative analysis by comparing our metrics versus the baseline metrics. We also have a qualitative evaluation by discussing the matches and mismatches between the layout pictures versus the metric values. Note that these are subjective judgments from authors. For the specific procedure, we generate 56 graph layouts with different datasets and algorithms. We compute the area, sprawl, Sprawlter, and baseline previous metrics on all these layouts. And we provide a layout, all the layout pictures and metrics in a supplemental table. We have detailed assessment of metrics with regard to the layout characteristics in the paper. And here in this talk, I'm going to pick a few examples. So the 56 graph layouts contains 38 synthetic ones and 18 real-world ones. In terms of the scale of the graph, we have a number of nodes from 50 to 5,000, and number of edges from 150 to 10,000. The layout algorithm we use include manual positioning, mainly for debugging and illustration, and some single level layouts and multi-level layouts. So here I'm going to introduce a few examples. The first one is about increasing overlap between node. You can see that from left to right, the blue nodes and the red nodes are have increasing overlap with each other. This is reflected by our area-aware clutter. So it's 4.3 less than 14.4 less than 13.6. For the count-based metric, it fails at the second case where it counts 1 crossings between the red and blues, which that lacks the ability to distinguish between the first case and the second case. When we further break down the total metric by the penalty for meta nodes and penalty for leaf nodes, we will notice that the contribution for the penalty of meta nodes are becoming heavier from left to right in our clutter metric. which is also reflected in the layouts because metanodes are more visually salient. Second case is about two variable node size layouts. In the first one, there are some clutter between the nodes, but it's less sparse than the right one. So for clutter, our metric and both our metric and the baseline tells a story about some clutter on the first one and no clutter on the second one. But for sprawl, the first one is much less than the right one. When we combine the area clutter and sprawl, we can see that the Sprawlter metric is, for the first one is 10, for the second one is 40. So this metric actually reflects the quality of these two layouts. The third case is about the real-world graph using multi-level layout. In the first layout, it's lower, the clutter is lower, but the sprawl is higher, and the other way around on the second one. This is reflected by both the area clutter and count and the sprawl metric. In this more complicated case where you have flipped relationship between clutter and sprawl, it's more important to have a combined metric. So our Sprawlter metric prefers the second layout because it has much less sprawl. The next example is about increasing overlap between nodes and edges. In these three layouts, we can see that blue nodes are intersecting with the edges more and more. So both the area-aware clutter and baseline metric reflects this fact by increasing the metric. But when we break down the total metric by penalty for metanodes and penalty for leaf nodes, we can also see this trend, which I mentioned before, that the penalty for meta nodes are contributing more and more in this metric, which is more aligned with the layout pictures. This is the last example about edge-edge crossings in a real-world graph using multi-level layouts. You can see that on the left layout, there are many orthogonal angles in the crossings, and there are many glancing angle crossings on the right layout. So both our area-aware clutter and count-based metric are successful in describing this situation. For future work, we want to incorporate the Sprawlter metric into layout algorithms, achieving the ultimate goal of making good layouts. We also want to incorporate more families of readability metrics beyond clutter and sprawl. In this work, we are using length to measure an edge, but we also want to incorporate meta edges with 2D area. To conclude, we propose an area-aware Sprawlter metric, which can account for geometric overlaps beyond integer crossing counts. It can deal with multi-level layouts by design, and it can handle the trade-off between sprawl, geometric sparseness, and clutter. You can find more details in this website. Thanks for watching. Thank you.